Hey guys, and welcome to Calculus. Hey guys, and welcome to AP Calculus AB Transcendental Functions. Today we're going to be talking about indeterminate forms. By the end of today's lesson, you should be able to evaluate indeterminate forms using L'Hopital's rule. We're in section 8.7 in the book if you want to follow along in the book, and everyone should be working on their transcendental functions homework packet. So far, we've already covered indeterminate forms. However, the only indeterminate form that we've looked at so far is 0 over 0, but there are others. In particular, infinity divided by infinity, 0 times infinity, 1 to the infinity power, 0 to the 0 power, infinity to the 0 power, and infinity minus infinity. These are all actually examples of indeterminate forms. These are all actually examples of indeterminate forms. Luckily for us, the mathematician L'Hopital came up with a rule to help us evaluate all forms, Luckily for us, the mathematician L'Hopital came up with a way. Luckily for us, the mathematician L'Hopital came up with a rule to help us evaluate indeterminate forms using limits. L'Hopital's rule is given as follows. L'Hopital's rule is given as follows. Given that f of x and g of x are differentiable on the open interval a to b, except possibly at c, and if the limit of f of x equals 0 and the limit of g of x equals 0, or if the limit of f of x is infinity. So L'Hopital's rule is given as follows. Given two functions, f of x and g of x, and that L'Hopital's rule states the following. Given two functions f and g of x which are differentiable on the open interval a to b, except possibly at c, and either both the limit as x approaches c of f of x and g of x equals 0, or the limit as x approaches c of both f of x and g of x equals positive or negative infinity, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of the derivative of f divided by the derivative of g. Simply put, this rule tells us that if we have an indeterminate form of 0 over 0 or infinity over infinity, of course disregarding the positive or negative, we just need to differentiate the numerator and denominator and then take the limit. In order to evaluate this, we just need to differentiate the numerator and denominator and then take the limit. For now, we'll look at the indeterminate forms of 0 over 0 and infinity over infinity. Let's say, for example, we have the following. Find the limit as x approaches 0 of 3 cosine of x minus 7x minus 3 all over 10x. Of course, since this is a limit, the first thing we should probably do is try to use direct substitution. If we use direct substitution, 3 times cosine of 0 is 1, is 3, minus 7 times 0 is 0, minus 3. So in the numerator, we end up with 3 minus 3, which of course is 0. In the denominator, the limit as x approaches 0 of 10x is also 0. We do want to evaluate each of these limits separately and individually. We must show this step on the AP exam. We must show the limit as x approaches 0 of the numerator is equal to 0, and we have to show that the limit as x approaches 0 of the denominator is also 0. Since these are both 0, we can apply L'Hopital's rule. According to L'Hopital's rule, we just have to take the derivative of the numerator and the denominator. The derivative of the numerator is negative 3 sine of x minus 7. The derivative of the denominator is 10. Once again, we could go ahead and use our direct substitution. If we use direct substitution, we're left with negative 3 sine of 0 minus 7 over 10, or negative 7 over 10. Or negative 7 over 10. Let's look at another one. Let's say we want to find the limit as x approaches 0 of e to the x plus e to the negative x minus 2 divided by 1 minus cosine of 4x. Once again, we want to use direct substitution and see what happens. If we apply the limit as x approaches 0 to the numerator, we get 0. E to the 0 power, of course, is 1, plus e to the negative 0 power is still 1, so we get 1 plus 1 minus 2, which of course is 0. If we find the limit as x approaches 0 of the denominator, 1 minus cosine of 4x, we get 1 minus 1, which is also 0 if we apply direct substitution. Since both the numerator and the denominator give us 0, we can apply L'Hopital's rule. If we find the derivative of the numerator, we get e to the x minus e to the negative x, all over 4 times sine of 4x. Once again, let's go ahead and try to apply direct substitution. If we do so, we get e to the 0 minus e to the 0 over 4 to the sine of 0. If we do so, we get e to the 0 power minus e to the 0 power divided by 4 times sine of 0, and which of course gives us 1 minus 1 over 0, or 0 over 0. That means that we can apply L'Hopital's rule one more time. Once again, we must show that we've applied the limit to both the numerator and the denominator separately. Once again, we must show that we've applied the limit as x approaches 0 to the numerator and the denominator separately. So the limit as x approaches 0 of the numerator is 0, and the limit as x approaches 0 of the denominator is 0. Since both of these are 0, we can apply L'Hopital's rule a second time. If we do so, we get the limit as x approaches 0 of e to the x plus e to the negative x, all over 16 cosine of 4x. We're going to try to do direct substitution one more time, and we get e to the 0 plus e to the 0 over 16 times cosine of 0, which of course is 2 over 16, or 1/8. Let's try this one. The limit as x approaches infinity as, let's try this one. Let's try to evaluate this one. The limit as x approaches infinity of e to the x divided by 5 times x squared. If we try to use direct substitution, we'll see that the numerator gives us infinity. If we try direct substitution in the denominator, it also gives us infinity. Since they're both infinity, and we don't care if it's positive or negative, we can disregard the sign, then we can apply L'Hopital's rule. If we apply L'Hopital's rule, the derivative of e to the x, of course, is e to the x, and the derivative of 10x is just, and the derivative of 5x squared is 10x. If we apply direct substitution, we get e to the infinity over 10 times infinity, or infinity over infinity again. Again, since we have infinity over infinity, we have to show that we applied the limit to both the numerator and the denominator. Once we've shown that both the numerator and the denominator both becomes infinity, we can go ahead and apply L'Hopital's rule a second time. If we apply L'Hopital's rule again, we get the limit as x approaches infinity of e to the x divided by 10, which of course is infinity over 10, or just infinity. Let's try another one. Let's evaluate the limit as x approaches infinity of ln of x minus 3 over 2 radical x. If we apply the limit as x approaches infinity to the numerator, we get infinity. If we apply the limit as x approaches infinity to the denominator, we also get infinity. So that tells us that we can apply L'Hopital's rule. If I find the derivative of the numerator, I get 1 over x. If I find the derivative of the denominator, I get 2 over 2 rad x. Of course, we could simplify this, giving us rad x over x, which of course is just 1 over rad x. If we apply the limit to this is bottom heavy, we're going to see that the limit is going to be 0. L'Hopital's rule tells us that we could also apply L'Hopital's rule to other indeterminate forms, specifically 0 times positive or negative infinity. These limits will initially have the form of the limit as x approaches some value c of f of x times g of x. However, they're going to produce an indeterminate form of 0 times positive or negative infinity. In these cases, we're going to have to convert the product into a quotient. We know that multiplying two values is the same as taking a value and multiplying. We know that when we have two fractions and we're dividing, we could just turn the division into a multiplication, into a product, by multiplying by the reciprocal. We could also do the opposite. If we have a product, we could turn it into a quotient by dividing by the reciprocal. So the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x divided by 1 over g of x, or we could do the limit as x approaches c of g of x divided by 1 over f of x. Once again, once this is a quotient, we will either have 0 over 0 or infinity over infinity, and we can apply L'Hopital's rule. Let's say, for example, we want to find the limit as x approaches 0. Let's say we want to find the limit as x approaches 0 from the right of x times ln of x. If we use direct substitution, we're going to get 0 times negative infinity. Of course, this is indeterminate, so we're going to want to rewrite it, and we're going to rewrite it as x as, and we're going to want to rewrite this, and we're going to rewrite it as the limit as x approaches 0 from the right of ln of x divided by 1 over x. We're going to evaluate the numerator and the denominator individually as x approaches 0 from the right. The limit as x approaches 0 from the right of ln of x is equal to negative infinity, and the limit as x approaches 0 from the right of 1 over x is infinity. Since they're both infinity, and we don't care that one's positive and one's negative, we can apply L'Hopital's rule. If I find the derivative of ln of x, I get 1 over x. If I find the derivative of 1 over x, it's negative 1 over x squared. I'm going to go ahead and simplify this and turn this into the limit as x approaches 0 from the right of negative x, which of course, if we use direct substitution, is just 0. Let's go ahead and try that one more time. Let's find the limit as x approaches negative infinity of x times e to the x power. If we use direct substitution, we're going to yield negative infinity times e to the negative infinity, or negative infinity times 0. So I'm going to turn this into a quotient. If I turn it into a quotient, I could turn it into the limit as x approaches negative infinity of e to the x divided by 1 over x. I'm going to evaluate both the numerator and the denominator independent of each other, and I'm going to get the limit as x approaches negative infinity of e to the x power is equal to 0, because e to the negative infinity is 1 over, because e to the negative infinity is 1 over e to the infinity, which is bottom heavy, which is going to be 0. The limit as x approaches negative infinity of 1 over x, of course, is also 0. We can apply L'Hopital's rule. If we apply L'Hopital's rule, the derivative of e to the x is e to the x, and the derivative of 1 over x is negative 1 over x squared. If we try direct substitution, we're going to get negative. If we simplify that, we're going to get the limit as x approaches negative infinity of negative x squared times e to the x power. If we use direct substitution, we'll see that it actually gets worse. If we apply direct substitution, we actually see that this is actually getting worse. We still get infinity times 0. What that tells us is that we probably should have put the other function in the denominator. So let's try this one more time. This time, we're going to put x in the numerator, and we're going to put 1 over e to the x in the denominator. If we do this, we still get the limit as x approaches negative infinity of x is negative infinity, and the limit as x approaches negative infinity of 1 over e to the x is infinity. So we can apply L'Hopital's rule. If we apply L'Hopital's rule, however, this time we're going to get 1 over negative 1 over e to the x power. If we simplify this, we get the limit as x approaches negative infinity of negative e to the x power, which of course is 0. Let's try one more. Let's try another. Let's say we want to find the limit as x approaches pi over 2 from the left of 2x minus pi times secant x. If we use direct substitution, we get 2 times pi over 2 minus pi times secant of pi over 2, which is 0 times infinity. This means that we're going to want to rewrite it, and I'm going to rewrite this as 2x minus pi over 1 over secant of x. But everyone should know that 1 over secant of x is just cosine of x. We're going to go ahead and apply the limit of both the numerator and the denominator separately, and we get the limit as x approaches pi over 2 from the left of 2x minus pi is 0, and the limit as x approaches pi over 2 from the left of cosine of x is also 0. Since these are both 0, we can apply L'Hopital's rule, and we're going to find the derivative of the numerator and the denominator. And we're going to find the limit as x approaches pi over 2 from the left of 2 over negative sine of x. If we apply direct substitution, we get 2 over negative sine of pi over 2, or 2 over negative 1, which of course is negative 2. Now, there are other forms of there are other indeterminate forms, specifically 1 to the infinity power, 0 to the 0 power, and infinity to the 0 power. These limits will initially have the form the limit as x approaches c of f of x to the g of x power. The limits will produce the indeterminate forms of one of the following three. 1 to the infinity power, 0 to the 0 power, or infinity to the 0 power. In these cases, we'll have to convert using logarithms. However, that's beyond the scope of calculus AB. However, these cases are not covered in calculus AB. However, these cases are beyond the scope of the AP Calculus AB curriculum. And we will continue this lesson in AP Calculus BC, or for those of you guys who go on in math, you'll continue to study this in your subsequent calculus classes. Thank you for listening and thanks for watching. I hope that you enjoyed this lesson.